the attitude horizon in certified airplanes, that's a way better option than the $24,000 unit.
So it's just getting signed off and approved, that's.
Well, it's because of these new changes to Part 23 that are allowing performance-based specifications. So Dynon has proved without a TSO. A TSO lays out every detail of the component and how it will be manufactured. Performance-based says it will operate and meet these parameters. We don't really care how you got there. Yeah. So
See how that works for them when if they start to have issues with them, I can see that's not gonna be a good thing.
well, then they'll come back around and fix it. I think it's a way a lot better. You think about the situational awareness that the pilot is getting from this.
Getting more info.
Far outweighs the potential for some problems that are gonna occur, that we're gonna see occurring anyways. Particularly when the given equipment that it's replacing is no longer being manufactured.
Okay.
Here's another component. This, remember all that engine data I was showing you there? It's all coming from this little magic box. Okay? These guys are all your engine sensors. These guys are all your CHT probes. So all of these probes right here are being fed CHT and EGT. All of this data, potential data, is fed into this unit.
Wow.
A serial port comes out the other side and runs to the display unit. That unit right there can be mounted on the forward side of the firewall. So you only need to run 4 wires through the firewall. Okay? Significant advantage here. Instead of having all those thermocouples and all those wires running through a big hole in the firewall, all you've got to have is the data going back and forth. This particular magic box analyzes everything. And each one of these guys, while it gives you some common values, you can reprogram any one of these values to have it do whatever you want it to do. And in fact, it may call upon you to be the guy that has to reprogram those. So all kinds of setup configurations that you're going to have to do between what it physically looks like, what it looks like in 100% screen mode, 50% screen mode, 20% screen mode, whatever modes it has available, what the operating values are. So let's say oil pressure. My oil pressure, I'm going to have it read from, say, 20 psi all the way up to 250 psi. And then where's my red line? And where's my yellow line? And where's all those parameters you pre-program in? You also may need to do some calibrating. So for example, the fuel level transducer. The fuel level transducer is going to be a wire that goes out to a little resistive or capacitive element. It's looking for a specific amount of resistance per gallon of fuel. Well, you don't know what that is given the shape of the fuel tank, the dihedral of the wings, or the fuselage, or anything. You have no way of being able to calculate what that is. This particular unit, most of them are going to be looking for a value of 0 to 5 volts. Almost all digital electronics operate on 0 to 5 volts. So based on whatever the resistive sensor is doing, it's going to vary the voltage from 0 to 5 volts. So instead what they'll do is saying, well, you don't know what that is, so we're going to take it a different way. We're going to calibrate it. You're going to empty all the fuel. You're going to turn the thing on and start the calibration routine, and you're going to put in the unusable fuel. Push a button. Then you're going to put a gallon in. Push a button. Put a gallon in. Push a button. Put a gallon in. Push a button. And you're going to keep doing that all the way until the tank is full. Or you may also have a little problem in there in that the fuel sensor may not measure a full tank. So for example, if your wing, your wing tank is shaped, leading edge of the wing is shaped like that, well, the fuel sensor sits right here with its little float that goes up, and it hits up here, so right there, when the fuel level is right there, it's gonna say full. So it can't measure the last 8 gallons of fuel that goes in there. However, you're gonna tell the fuel computer, because it's also measuring fuel flow, that it carries 16 gallons, but you're gonna tell, when you calibrate the gauge, that it's got 8 gallons at this point. Then what it'll do is, as you're flying along, it'll say 8 plus, and it'll stay 8 plus until the flow sensor starts coming down. Okay, then it'll drop the plus, and then go from 8 to 7.9, 7.8, or whatever. Again, all calibration routines you may have to do as you go to install this kind of a system. Okay. It's reasonably, once you sort of do this for a while, you come to realize that there aren't that many kinds of sensors. What have I talked about so far? A thermistor, a thermocouple, some pressure switches, okay, and then a few digital devices like the flow scan device. So ultimately, you begin to get a sense of what kind of, by knowing what kind of data is being measured and the number of wires, you can get a pretty good sense of what type of sensor it is. If I've got one wire that goes and it's measuring temperature, one wire measuring temperature, I know it's a thermistor. Not only do I know it's a thermistor, but I know what its voltages are going to be. Voltages are almost always going to be 0 to 5 volts, unless it's an older thermistor type, in which case it'll be 0 to 12 volts. Okay? There's no other magic out there. This is the magic that exists, even though there's a million different packages and they all look different. They all have to work the same way. They all have to work in the same voltage range. Okay? They will almost always work in the same resistance range as well. Okay, most of your thermistors operate from 30 to 3,000 ohms. There's a few that go up to 5,000 ohms. And the 5,000 ohms will be cold, the 30 will be hot because they're negative coefficient. 3-wire sensor commonly puts out digital data. Sometimes they'll put out an analog signal. One of the wires will be ground, one will be 5 volts, the other will be a variable voltage, 0 to 5 volts, either digital or analog. And I can go down a long, long list of different sensors, and those two that I just covered will cover 80% of them. Thermocouples, throw thermocouples in there, and I've covered about 95% of them. However, sometimes it's a little difficult to get what known good values are supposed to be. Now, one of the things that's really cool about the Dynon there I showed you is one of the setup screens. It allows you to go in, pick the sensor, and it gives you actual hard data values in real time. So you can sit in there and look at hard data value for the fuel flow sensor or for the fuel float level, and it'll be sitting there, 3.4. You start rocking the plane, 3.4, 3.2, 3.4, 3.6, 3.4, as you're rocking the plane and the fuel's sloshing back and forth. Makes it a lot easier to diagnose what's wrong. But you do have to understand how the system works. So it's a little difficult, but most sensors will provide an analog data, an analog voltage value. Now, when I say voltage, it's a very small amount of current. We don't want this thing to send a bunch of current through any sensor. That's just making the generator work hard, right? So each one of these sensors are typically only going to drop maybe a milliamp or 2, maybe 3 milliamps of current. Pretty high impedance circuits. So all we're looking for is a variable voltage, and it'll typically be in an analog form. There are some instances where a sensor, because of erroneous RF and other interferences that can occur, they'll design the sensor to have its own little computer in there. So, for example, many of you guys in your ignition systems, when you still had a distributor rotor in there, like the Ford and the GMs had a distributor rotor spinning around, well, the secondary ignition was produced enough RF that the little capacitive discharge sensor in there would sometimes get interfered with the data going out. So what they did is they installed what's called a little Hall effect sensor, which is a little magnetic sensor, and they were going to feed power and ground to it anyways, so they sent it a little computer. And the little computer was an analog to digital converter that sat in there. And it just read the Hall effect data and switching data back, on, off, on, off, on, off, on, off, on, off, data back. So instead of being analog like this, it translated it into this. Okay? And then the data that showed up on the signal line going back to the main engine control unit was digital data of some kind, synchronized to a specific clock speed. Okay? So, most of the time, we sense directly to the computer with analog data, let the computer itself digest that, convert it to digital, and do whatever it needs to. The only time we typically convert it to square wave or digital waveform is when there's problems with communication problems. So you need to make it a little bit more robust communication platform. Now, different devices do different things. So, for example, on your computers, your keyboard is essentially an analog to digital converter. Every time you push a key, it's got its own little computer in the keyboard that says, okay, I'm going to send a blip of data that looks pretty much like this. Okay, blip of data, binary data that goes up to your computer. The computer decodes that binary data on the ASCII table and says, oh, they pushed the number 1 or the M or the capital M key. You push Shift M, it translated into ASCII for capital M. So that's an example of a sensor, the keyboard, taking input, converting it to a digital signal, and transmitting it to the computer. So any digital sensor always requires power and ground. We commonly call that VCC and maybe VEE for reference. Oftentimes that won't be, you don't get to pull out your 5-volt battery and hook it up. So one of the things you will install, you'll hook up power, you'll hook up ground, you'll hook up all the different sensors, and there'll be 2 outputs from the computer. One of them will be VCC and one of them will be VEE. That may go to a separate bus that then powers up all the different sensors and provides ground for all the sensors. Okay, that ground will not be the same ground as the airframe ground. Okay, that'll be an isolated ground. I'm going to dive too deep into how they do that, but you don't want to try and ground anything else through that. Okay? Nor do you want to take any of the sensors that require VEE and ground them through a normal, ground them to chassis somewhere. Because if you have any stray ground voltage going on, you're suddenly going to be adding that voltage to whatever the input driver is for that sensor data, and they sometimes can't handle that all that well. Okay. The other advantage of this kind of technology is the fact that they can be networked. So you remember that little box. Okay, I can also have a separate little box that's my comm radio, and a separate little box that's my transponder, and a separate little box that's my engine module, and another little box that's the attitude horizon reference sensor, another little box that's the electronic compass sensor. Okay, 2 little boxes that are just autopilot servos, right? And all of those guys can operate on a serial network. Okay, serial network is no different than anything you hook up USB. Okay, USB, Universal Serial Bus, is a serial network. You're going to have VCC, which will probably be 5 volts. You'll have VE, which is going to be a ground. You're going to have TX and RX, transmit and receive. And in fact, in the RS-232, the pin numbers are pretty standardized in there. I won't say what they are because I don't know how many pins you've got in your typical connector. But then what's going to happen is anytime anybody says, hey, I want to talk to the, what do I want to say? Let's say, how about I want to talk to the vertical servo, vertical autopilot servo, one running the elevator. It'll say vertical autopilot in some digital data footprint. Here's a set of instructions. All the different users on the network are listening and they say, well, that's not me. That's not me. The vertical autopilot servo says, hey, that's me. I'm paying attention. Okay, I'm listening to it. Then what it's going to do is it's going to listen to what it heard. It's going to run through an algorithm to make sure that what it heard makes sense in the standard communication protocol to cross-check error. Then it's going to say, all right, this is what I heard and send it back. There'll be a heartbeat communication going on as well. The heartbeat just says, I know that the motherboard computer hasn't died, and the motherboard computer is listening to everybody else's heartbeat and saying, I know you haven't died. It's a way of error checking. And in fact, in more complex systems, what will happen is if you get a heartbeat error, they'll have multiple computers, and one of the other computers will take over. So, for example, Pratt & Whitney 4000, there's 4 computers on board. They're all watching each other. They're all watching each other's heartbeat. And if it starts getting a heartbeat error, is considered a catastrophic error. The other 3 will gang up on the one that's got a heartbeat error and shut it off, take it offline. Big red light in the cockpit. Not necessarily mayday, mayday, but still going to need maintenance. All right, so data logging is pretty good. Monitoring is pretty good. They've actually got systems now. I don't say actually got. They've had them for the last 30 years, where the more expensive equipment, you know, Southwest, you got to know about the time that if I forget her name already, realized she had an engine failure. Her company on the ground already had the data downloaded. Okay, they're doing real-time monitoring of engine parameters on most of the newer generation airplanes. Okay, that information happened pretty darn quickly, particularly once the plane flagged an alert. They can tell pretty universally, as long as the engine's operating, you know, isn't disintegrating like that one did, when the engine's due for being having major maintenance. Okay, exhaust pressure ratios are starting to get below a certain value. They can say, okay, the way this thing's declining, May 1st, when the plane lands in Albuquerque, we need to have a left engine there ready to go. Bada bing, poof. Makes life a whole lot easier. I have, when was it? The 1996 Olympics. I was in Atlanta doing some training for a commercial operator, the Metro Atlanta
MARTA?
Rail, yeah, MARTA, Metro Atlanta Rail Transit Authority, something like that. I was doing some training for them. They were converting over to natural gas stuff. They did some stuff that was pretty honky-dory. And I recognized what they'd done and managed to convince the engineers that what they did was really stupid. Went down to literally went down to Radio Shack, bought a bunch of big ass resistors, plugged them in and caused the systems to work a whole lot better. That actually won over all the technicians. They were like, how did you know? And I was like, how did I know? It's basic Ohm's law. Let me tell you about this thing called Ohm's law and show you how I knew. But one of the things that was really cool was a couple of the drivers kept saying, these things aren't getting the mileage we're getting. And the engineers kept saying, you're driving too fast. And the drivers kept saying, we're not driving too fast. These things aren't getting the mileage you said they're supposed to get. And the engineers said, you're driving too fast. Finally, I said, I said to the drivers and all the rest of the mechanics, if they're telling you they're driving too fast, that's because they're watching you drive too fast. Well, what do you mean? Finally, the engineers fessed up, opened up their laptop, and there were all the buses in the city, where they were and how fast they were driving. Real time. Okay. Oh yeah, everybody, all the drivers, the word went around real quick. Uh-oh, their big brother is definitely watching us. Real time. Make no mistake. I can tell you right now, if you go down here to San Diego, Lindbergh, and drop your car off at the low Pacific Coast Highway parking place there, and you jump on the little shuttle that goes all the way around the airport, shows up and drops you off. If that shuttle goes over 25 miles an hour, it automatically sends a signal directly back to home base. Those guys get 3 warnings and they're fired. Yep. I mean, it's now. Are we there yet in our cars? Actually, there are some cars that have a 30-minute FIFO onboard chip. At this point, my understanding, the current laws are that they cannot use it for criminal prosecution, but insurance companies can actually use the data on some vehicles. So that trend is not going to change. It's only going to get more and more. And from our perspective, it's extremely useful data. So here's kind of what it looks like. That's pretty meaningful, huh? Look at all those numbers. Okay, well, we've got system time and oil pressure and oil temp, and man, look at all those. And note, by the way,
That'd be 30 seconds.
it looks like, I don't know what that is, but it looks like 20 or 30 samples per second, something like that. Sampling at a pretty good clip. Got all kinds of stuff, takt time and volts and fuel and map and CHT and EGT. The other thing I can do is I can download it. There's a pretty cool website. Actually, I'm cool. I then did this. This is a bunch of flights I've made. So it records all the flight data, including engine data. So here on this date, at this time, I flew from French Valley to Gillespie Field. That's the number of the airplane. That's actually erroneous. That's the correct value. Duration of the flight was 32 minutes. Then if I go in, and it's sort of giving a flag. CHT was high. When I look at the hard data, this shows, in this particular case, I'm looking at, and it's a little hard to see, but I got EGT flag here, CHT flag there. In this case, I've got fuel flow flag down here in the blue, and then over here, I've got map flag here. So in this case, you can see I dropped the throttle in here. Map went way up as the throttle went in, and fuel flow went up. Here, it looks like throttle was coming down, or I don't know what I was doing. Clearly here, it looks like fuel flow was really low. Probably run up here, went way up, came back down, took off. Same thing here, map was low until the engine started, and then it kind of and then map was here. EGT, again, engine running, not too high. As I started to bring the power up, EGT starts to climb. Then somewhere in here, it started to separate and deviate. Well, this particular system, online system, allows me to then zoom in. Let's say there's an anomaly there. I can zoom in and look at that anomaly a lot closer. And I can add, and in this particular case, I happen to have the cursor right, I was holding it right there when I took this snapshot. So it's giving me the actual values for each of these at that point. So, you know, let's say I had a fouled injector. One of these might be completely different. They're reading quite a bit lower than normal, right? Here it took the electronic flight information system. This shows my actual flight plan. So what I did is I took off from here at Gillespie, went out and did the test flying, came back and went all the way down to Brownfield, got gas, and then came back. The flight plan, what I was, in this particular flight, I was actually doing a bunch of propeller testing. So what I was doing was flying a heading of 0, 120, 240, 0, 1, 2 times, 2 minutes with 1 minute turns. And this area happens to be fairly smooth. And I can fit in between a hole between the Camp Pendleton airspace and the Class B airspace right here. So the first run is at 8,000 feet and the next run is at 4,000 feet. So this was kind of fun, getting from 8,000 feet to 4,000 feet. Put it in a knife edge, put it up to 5 Gs, hold the stick back. That apparently causes Tracon to get upset. They get a little nervous. It's kind of hard to see, but the lagoon is right here, and Class B airspace is right here. This big line right there. At I think it goes, I forget, it goes down to 6,500 somewhere in there. Well, right there, when I went, came down, I was below the shelf, but they were still seeing me up here because I came down so darn fast that when I came out here, they thought I blipped into their airspace. But once they went back and looked at the hard data, they then realized, oh wait, he was below, the transponder showed he was actually below the shelf. That got the, hey, you need to call so-and-so after I landed. I said, no, I don't. I didn't go in your airspace, and I can prove it right there. I was very nice to them, and they were very nice back to me. The truth is, it doesn't matter if I can prove it. It doesn't matter if their data is wrong and erroneous. Their ruling so far have been, our data is the only thing that matters. And even though I've got 5 GPS systems on board that all show otherwise, their data is the only thing that matters. We'll see how that plays out. I'm waiting to see a violation occur under the new Pilots Rights Act. Part of one of the things that occurred with all of this data systems was there was a guy flying an airplane very similar to mine, only he happens to be a U.S. Senator for the state of Maine. He was on an instrument flight plan, approved, he's a U.S. Senator, approved clearly by Homeland Security to fly into Washington, D.C. and land, because he's a U.S. Senator.
Right.
They violated him, they almost shot him down. Then they found out he was a U.S. Senator.
That would have been neat to see on the news. How they would have spun that story.
They really screwed up. They dropped the ball entirely, and that's to our fortune. Though it took them about 4 years.
Even though he had an approved flight by a foreign plane.
At all, yeah. He
So
was exactly where he was born.
people watching him were supposed to know that, correct?
ATC dropped the ball in communicating it to Homeland Security.
Ah.
Homeland Security.
I said, hey, who's this? You don't know.
Yep.
Shoot him.
Yep. Anyways,
What do they got to
you
shoot
guys
at
are going
you?
to have to become experts at this if you're going to work in our industry. Okay, it's already throughout general aviation in the form of airlines. I think some of you guys that have military backgrounds have already seen some of this, some elements of this. It's already strewn throughout general aviation, particularly in the experimental world. In fact, the last people to sort of get this technology is going to be the Fed themselves, FAA. They're still a little bit behind the times on some of this stuff. But the good news is they're saying, you know, this is pretty cool technology. Let's start certifying to put these in airplanes, you know, allowing or changing the certification process to allow this stuff to be installed in airplanes. For us, that's easy money. Doing this kind of work, these kinds of installs, is way better than changing hot oil filters. I gotta tell you, I've done both for a living. This stuff's way, way better. All right, let's break here. Let's solder.